Hey guys, welcome back from break. We're going to start off a little bit easy today and just introduce a concept that we're going to be using through the next couple units called dimensional analysis. With dimensional analysis, we're going to be working with conversion factors. These are quantities that can be expressed in different ways. So it's equal to the same total amount, but the units may be different. So for example, if I say I have $1, I might have a $1 bill, or I might have 4 quarters, or 10 dimes, or 20 nickels, or 100 pennies. They're all equal to the same quantity, but just in different forms, and they have a different unit. Same thing if we said that we have a piece of fabric that is a meter long. That could also be measured as 10 decimeters, 100 centimeters, or 1,000 millimeters. It's still the same length, but different units that are still equal to the same overall amount. So whenever two measurements are equal to one another, we can set up a ratio of those measurements that are equal to 1. So they do end up as the same quantity. It just simply ends up changing the unit. So for example, we know that 1 meter is equal to 100 centimeters. So that could be a ratio that we could use. If you're cooking and maybe something calls for tablespoons, but you only have teaspoons, you could still measure out what you need, knowing that 3 teaspoons are going to be equal to a tablespoon. So you could set that up as a ratio. These ratios that are equal to each other are known as conversion factors. So they will allow you to change between units without changing your overall quantity. So here's what some of this will look like. Sorry, my computer's being slow. So dimensional analysis is just a way to solve these problems, changing our unit of measurement without changing our overall quantity. So we're just going to go through a couple of very basic examples, things that you might do in everyday life. So for example, your school club has sold 600 tickets to a chili supper fundraising event, and you volunteered to make all the chili. Well, I don't have a recipe for 600 servings of chili, but my chili recipe can serve 10 people. So I have to know how to scale that recipe to feed 600 people. My recipe calls for 2 teaspoons of chili powder, so I need to know how much chili powder I'm going to need to cover 600 servings. So you first want to think of what things you know based off of what's given in the problem or just known conversion factors. And then you're actually going to solve for your unknown or what you're looking for. So you kind of want to look for the actual question at the end. There may be other information within the whole statement, but it really wants to know how much chili powder we need for 600 servings. So we know that we need 600 servings, and we need to know the total amount of chili powder in teaspoons. The only other bit of information that was given in the question that's useful is that your recipe that serves 10 people, so 10 servings, calls for 2 teaspoons of chili powder. So how you would set this up as a dimensional analysis problem to solve for how many teaspoons you need, you always want to start with what is given in the question. So we want to start with those 600 servings. And since we're looking for the amount of chili powder, you're going to set this up as a series of fractions. Sometimes you'll see this written as We call them railroad tracks. So it's just a series of fractions that are separated by lines. So I'll write it both ways. Either way, we're starting with 600 servings. In our answer, we don't need to know number of servings because we're looking for the amount of chili powder. So servings, think of in math. If you're trying to get rid of the fraction 1/4, you would multiply by the reciprocal. You would multiply by 4 because with the 4 on top and bottom of a fraction, they cancel. Well, we're trying to cancel the unit of servings. So since we're starting with servings, that unit needs to be in the bottom of our fraction. Well, the only thing I know that deals with servings is that my recipe for 10 servings contains 2 teaspoons of chili powder. So that will cancel out the unit of servings and leave us with teaspoons, which is what we're looking for. So we can actually punch this in the calculator, and any number on top of the fraction you're going to multiply. So in your calculator, you're going to do 600 times 2, and any number on the bottom of the fraction you're going to divide by. So we're going to divide by 10, and you should get that that is 120 teaspoons of chili powder. Excuse me, that was a little messy. So that's one way you'll see these written. Another way you may see these written is using railroad tracks. So it just has your baseline, which is that middle line of every fraction. You start with your 600 servings. There's just a line separating the different fractions. And same thing, servings goes on the bottom. Your teaspoons goes on top. And that's still going to equal the 120 because any number on top of the line you would multiply by. Any number below the line you're going to divide by. So you may see examples written both ways whenever you're going through some of these. Now let's look at our next example. Still dealing with the chili because I'm not patient enough to measure out 120 teaspoons of chili powder. I'd probably lose count. So it's going to be easier for me to measure this in maybe a cup or a pint, something of that form. So I want to know how many cups of chili powder I would need to actually measure out because that's going to be easier for me. I know that I'm starting out, I need 120 teaspoons, so that would be your starting point. Things that I know from cooking, I know that 3 teaspoons is equal to a tablespoon. And I also know that 16 tablespoons is equal to a cup. So we could actually measure out cups. This one is going to be a little bit more work because we have multiple conversions that we're dealing with. But regardless, you're always going to start with what's given. So we know we need 120 teaspoons of chili powder. Now, the conversion that I know, so I need to get rid of teaspoons because teaspoons is not my answer. So since I'm starting with teaspoons and it is on top of my fraction, if it makes you feel better, you can always put that over 1 if you don't like having that bottom spot blank. So since teaspoons is currently on top, that needs to go on the bottom of our next factor. The only thing I know that deals with teaspoons is that teaspoons can be equivalent to tablespoons. So if you look, we have 1 tablespoon is equal to 3 teaspoons. So that will get rid of the unit teaspoon. And now we would have tablespoons. Well, my answer specifically asked for cups. not tablespoons. So we need to add another step in, and we need to get to cups instead of tablespoons. So since we no longer need the unit of tablespoons and it's currently on top, that will go on the bottom of our next factor, and we can use that to change into cups. Now, from the conversions that I know, 1 cup is equal to 16 tablespoons. So that would cancel out the unit of tablespoons and leave me with cups. So once I have cups, which is the unit I was looking for, I simply need to put this in the calculator. Remember, anything on top of the line gets multiplied. Anything on bottom of the line gets divided. So to punch this in the calculator, we would do 120 divided by 3, which gives us 40. But we also have to divide by 16. So that's going to be equal to 2.5 cups. So that's going to be a lot easier for me to measure out than to sit there and count 120 teaspoons. Let's look at a more science-related example. The directions of an experiment ask each student to measure out 1.84 grams of copper wire, but the only copper wire available is a spool with a mass of 50 grams. How many students can do the experiment before the copper runs out? Now, some of these you're probably going to be able to do in your head. They're easy one steps, but still always show work for things like this. So we know how much copper we have, and we want to know how many students can do the experiment. So always start with what you know. We know we have 50 grams of copper. And we know that each student needs 1.84 grams. So since we don't need no grams in our final answer, that will go on the bottom of our next step. And we're looking for students as our answer. So that's going to go on top. So we know that one student needs 1.84 grams. So that will cancel out grams, leaving us with students. So we can put that in the calculator because we were looking for a number of students. Now 50 divided by 1.84 is 27.17 students. Now sometimes use a little bit of common sense. We can't have 0.17 of a student walking around, so you can simply say 27 students as your answer. Let's look at another one. Here's one similar to some problems that we did in Unit 1 with density that you can also solve using dimensional analysis. So this wants to know what's the volume of a pure silver coin that has a mass of 14 grams. And from our reference sheet, we know that the density of silver is 10.5 grams per cubic centimeter. So we know the density, we know the mass, but we're looking for the volume. So remember, always start with what you actually have. We know that our coin has a mass of 14 grams. And we're looking for volume. So we do not need grams in our final answer because we want to know volume. So grams will have to go on the bottom of our conversion factor. And our conversion factor is our density. We know grams related to cubic centimeters. So our density was 10.5 grams per cubic centimeter, make sure that that 10.5 does go with grams, and that's per 1 cubic centimeter. So that will cancel out the unit of grams, leaving us with cubic centimeters. So now we can simply put it in the calculator. We can do 14 divided by 10.5. So that's going to be 1.33 cubic centimeters. Now for honors, you can always do sig figs with dimensional analysis problems. Whenever you are using significant figures, the digits in the conversion factors don't really matter. You always want to pay attention to your original number. So here we were originally told that our coin had a mass of 14 grams. That has two significant figures. So your answer, you would want to round to two significant figures. So you can actually report this as 1.3 cubic centimeters, and that would be your answer with sig figs. Let's look at one more example. So sometimes you're going to come across problems that you don't necessarily know all of the conversions off the top of your head, but you want to be able to break it up into more manageable chunks and things that you do know. So we want to know how many seconds are there in exactly one day. This is not something that I know off the top of my head, but you can get there with different things you do know. So we have one day, and we ultimately want to figure out seconds. So we're going to start with one day. Now, I don't know how many seconds are in a day. I don't know how many minutes are in a day. But I do know that one day is equal to 24 hours. So that would be my first step I would do. Since we do not need day as part of our answer, we have to get rid of that unit. So it will go to the bottom. And I know that one day is equal to 24 hours. So that will cancel out my unit of day. Now I'm looking for seconds, not hours, so I'm not done yet. Off the top of my head, I don't know how many seconds are in an hour. If you do, you can use that conversion, but if not, I'd say, okay, I don't know how many seconds are in a day or in an hour, but I know how many minutes are in an hour. So yet again, we're going to try to get rid of hours. So hour will go to the bottom, and we can compare minutes in an hour. So 1 hour is equal to 60 minutes. So that will get rid of my unit of hour. And now I have minutes, but pay attention, you're trying to get to seconds. So we know that 1 minute, and I'm putting it on the bottom so my units cancel, is equal to 60 seconds. So that will cancel out minutes and leave me with seconds. Once you have the appropriate unit, you're finished. You just need to put it in the calculator. So we'd say, okay, there's one day times 24 hours times 60 minutes in an hour times 60 seconds in an hour. So that's going to be a total of 86,400 seconds in a day. So these problems, all of this is getting used to the setup because we're going to use this throughout our next 2 units. But always make sure that you set it up so you can see the units cancel. So you should be writing out your units. And make sure that you're using the appropriate number. So you can't say that 24 hours is equal to 60 minutes because they are not equal. So it would have to be 1 hour is equal to 60 minutes. So you do not have to carry the same number throughout the entire problem. You're simply breaking it up into smaller chunks. Practice using this skill, and then we'll actually start using this with some scientific numbers tomorrow when we start MOL.